want to begin by saying that I made a very bad mistake the day before yesterday. I referred you to a book on functional analysis, and I gave the name of the author wrongly. The first name was correct. Second one, I was having in mind one time Prime Minister of Hungary, another time V. Srinivasan's close friend Imre Gyuk. So I said Imre Nagy, but actually it is Bela S. Nagy. I think it's called Functional Analysis. You probably have a book copy from the 60s. So it is a wonderfully written book, very, very nice. It is not easy, but it's still so beautifully written. And I mentioned that in this book they have, in the early part, constructed explicitly this Weierstrass function, which is a function which is continuous everywhere but cannot be differentiated anywhere. And so you may think that that is a very strange kind of function. What is the word? There is some word for it. Bizarre kind of function. But do you know there is a physical problem where such functions are involved? Brownian motion. So just saying that it is there in Brownian motion, still I don't understand it. But the paths of Brownian particles are continuous, but there is no velocity anywhere. So just wanted to say that this is not irrelevant in a physics context. Okay. Then we had started talking about the structure of Lie groups and Lie algebras, and we saw that the group composition law is given by a system of functions which gives the coordinates of the product of two group elements in terms of the coordinates of the individual factors. So these functions have two independent group elements as arguments. From them we constructed somewhat simpler functions, matrices of functions, and these depend only on one argument each, one group element. And we then showed that the group composition law given by these functions can be regarded as the solution to a system of partial differential equations. So you have to think of f of alpha beta as the unknown, and you imagine that the betas enter as the values of these unknowns at alpha equal to 0. Alpha is a multidimensional variable, R components. So now I would like to just show you examples of these functions eta and psi, so that they are not so totally unfamiliar. If you take an abelian group, which nothing could be simpler, and if you use parameters so that group composition corresponds to adding parameters, then what do you think psi eta will be? What will be this matrix eta? It's extremely simple. All of these things are the unit matrix. So you can verify this very easily. Psi is therefore also the unit matrix, being the inverse of this. The eta roof matrix also is unit matrix. I thought I would just show you the shape of these matrices for the case of the rotation group. I am using here both lower indices because it is adequate in this case, and I am using axis angle coordinates on the group. I don't expect you to derive this, but I just wanted you to have a look. This is the expression for the eta matrix in the case of the rotation group. It is fairly complicated. I mean, complicated in the sense it involves trigonometric functions. And you can easily invert this matrix, and then you will get the matrix psi. So just so that you have a feeling what these things might be. What does this look like? Psi is you don't have to write these down. I just wanted them to be visible so that you get an idea of what these things look like. I don't know these matrices for any other group myself. I have not calculated them. And I don't know if in books, in usual books, you get these expressions anyway. But it is all here, which is of course out of print. All right. So this is just to remind you of what we were doing last time. And if you don't mind, I will now rub these things out just to give you an example, a feeling for what these things are. You can see that these functions, the etas, it involves a hyperbolic cotangent, so it blows up somewhere or other. So you know that you must use it only in a suitable neighborhood of the origin. All right. So we discussed in some detail the content of this equation. We know that if we start with the associative law, and let me write it here. It is a system of functional equations obeyed by the group composition functions. And from there, we were able to derive these partial differential equations. And what I will now start today is to show you that actually, except for global aspects, if you start with the partial differential equations in alphas with betas appearing as boundary values, if those equations are consistent, and we will study consistency later, if those equations are consistent, then they have a unique solution f of alpha semicolon beta obeying those boundary conditions. If such f obtained by solving that equation, you put it in here, it will obey the associativity condition. So what we have achieved is give a differential expression of associativity. How do we do this? It's quite a nice exercise. It's not very complicated at all. We are given those partial differential equations, and we want to ask if this is true, question mark. So what we do is the following. Just for the moment, well, let me put the index here. Let me imagine that gamma is the running variable. The partial differential equation is written with respect to gamma. And for the moment, you suppress both alpha and beta. After all, that partial differential equation has as its running variables the first set of coordinates inside the function f. So I will use that fact here. So look at this left-hand side. what partial differential equation does the left-hand side obey with respect to gammas as the independent variables? We will use that. Instead of alpha there, we'll put gamma. Instead of beta there, we'll put this whole stuff. And so you will immediately find a kind of compressed notation. With respect to gamma, the left-hand side obeys this partial differential equation with that boundary condition at gamma equal to 0. All right. Now, let's ask, what about the right-hand side? Are we able to calculate a similar system of partial differential equations for the right-hand side? Now you see that gamma is sitting inside the F, so we have to use the chain rule. So for the moment, let me call this set of variables delta. So what do I have? I will write it slowly. I have to do a partial chain rule. That is, I want to differentiate the right with respect to some component of gamma. First I differentiate with respect to a general component of this whole thing which I have called delta, and then I will put in delta derivative. Do you see that this is correct? Huh? This one? Huh? I'm sorry. Yeah, it is. But I just wrote it in this form. Now, you use that relation. You can use it for this factor because it's a derivative with respect to the first set of arguments. You can use it here also, in both places. This is a clever trick. So what is the first factor? What does it give you? I will just write it in a compressed form. JL. Then I have eta. Sorry, I made a mistake, not gamma. Delta, eta of delta, psi of gamma, L, K. I am using that known partial differential equation from where I have constructed F. I have used it both for this first factor and for this second factor. And now see what magic happens. What is the whole thing here? As a product of matrices, eta of R, psi of delta, eta of delta, psi of gamma. L is summed over. Mani, something is not clear. J, L, L, K.
But then that side must be J, K.
Yeah, you are right. Yeah, perfectly right. I am running on very low horsepower today. Yeah, perfectly right. And now you see that psi and eta are inverses to each other. So what does this boil down to? Huh? Pardon? Where L only? Isn't this correct? Yeah. J is correct. J, L, L, K. This is correct.
First term we have delta
Yeah, OL. I'm sorry, I'm getting really confused. Yeah. Yeah. Sorry. This is the chain rule which is being used. So now you use the fact that the psi and the eta are inverses of each other. So two of the factors just vanish, and what is left? Just dictate to me. Eta of r, psi of gamma, j, k. And moreover, what value does the right hand side have at gamma equal to 0? At gamma equal to 0, what is it? F of alpha beta. So just look at the differential equation obeyed by L, the left hand side, and by R, the right hand side. They're identical. They, in general, are quite complicated. They are non-linear. But you can see the equations are the same. And therefore, solutions must be the same. And therefore, we have shown that if that partial differential equation on the right-hand side is a consistent system of equations, if we take the solution f of alpha beta from there, and if we try to set up a group composition law, it will obey the associativity property. That is what we have demonstrated. Is that all right? I hope I can now rub this out, all these errors. So so we have achieved what we wanted. Associativity is ensured by that system of partial differential equations. There is one more aspect which we must be clear about, and that is the association of an inverse to every element. And that is a little bit tricky. And let me just show you how it goes. The idea is that we are working in some neighborhood of the identity in the group or in the origin of Euclidean space, a region in which the matrix eta is non-singular, the matrix psi is non-singular. They are inverse to each other. So this Jacobian matrix is non-singular in the region where we are working. This means there is a theorem called implicit function theorem. If we ask, given alpha, will there be some beta such that f of alpha comma beta will be 0, component by component, every j? The answer is, again, if you are in a sufficiently small neighborhood of the origin, there will be a unique beta which will obey this equation. And so then we will say, I will give it a slightly different name. You will see in a moment why. I will say that if I had put in here the coordinates of an element A, and I solve these equations, and by the implicit function theorem I know there is a solution, I will then say alpha prime equals coordinates of A inverse. I'll just say so, okay, declare. So we are taking this function as a solution of these differential equations. We are using it to check associativity. Now we are in the process of checking whether inverses exist with the proper properties. If I do this, what property have I ensured? What relation between A and A inverse have I ensured? I have ensured A inverse equals E. This is what I have ensured. I have not ensured that A inverse A is equal to E. In this equation, alpha is chosen by you, alpha prime is then found as a solution to this equation, algebraic equations. Then you interpret alpha prime as being the coordinates of the inverse to this element, and this is all that you have shown. What about A inverse A? This is very, very clever. What you do is the following. I'll just write it as a flow chart, if you like. Start with an element A with coordinates alpha. Take the F which you have found by solving those equations. Set up these equations. Get values for alpha prime and say that they are the coordinates of the inverse on the right. We do not know at the moment whether A inverse A is E or not. We do not know whether if you take this solution alpha prime and put it in the first place and put alpha in the second, will you get 0? We don't know. So now you do the following trick. Start now with the inverse which you have just found. Plug that into the same formula. Put alpha prime in the first slot. Find alpha double prime. Then what should we say is alpha double prime the coordinate of? A inverse inverse. Write A inverse inverse. We can say this is true. Correct? And now we do the following. What is it that we have shown? We have shown from that partial differential equation, associative law is going to be valid. We will exploit that and combine it with this. So look at this relation. According to the associative law, we know that, see, in this whole manipulation, only the alphas are chosen by you initially. Alpha prime is determined, then from that alpha double prime is also determined. What do we know? What is this equal to? F of? No, what is the first argument? Alpha, semicolon alpha prime, semicolon alpha double prime. We know that this is sure. This is associativity. But now, this we know is 0. So what is the left-hand side? Alpha. This we know is 0. So the right-hand side is alpha double prime. So A inverse inverse is the same as A, right inverse of A. I leave it to you. So what does it say? It says that A inverse inverse equals A on the right, as a right inverse. All right? But what does this mean? Right? Always right inverse. But this is A. So I am home. It's a very clever trick, isn't it? So, just to repeat, if a group is given, these functions are in your hands. You have these simpler functions which you invent out of the group composition rule. You then arrive at that partial differential system. You now discover locally, if you start with this system, and if the system is consistent, that is, there is a solution, there is a way that the equations are not inconsistent, then you will get a solution F obeying that boundary condition. You can use it to define group multiplication. You can be sure it will have the associative property. You can be sure that inverses exist for each element, and the inverse of A can be put on the left or on the right of A. Both ways you will get the identity. So what have you done? You have reduced the problem locally of all group laws and group operations to that system of differential equations. Of course, the first person to have done all this, to have seen all this, was Sophus Lie, is a Norwegian mathematician. And there is a very nice book by a Russian mathematician and historian of mathematics, some Yaglom, I don't remember the initials. There are 2-3 Yagloms around, and this is one of them. Very beautifully written book. I hope, I'm sure your library has it. I don't remember the title, but you will love glancing through it. He describes the whole development of structure of Lie groups in the 19th century. And the interesting thing, which makes us feel not too bad after all, is that Sophus Lie had no idea about rigor in mathematics. He made all kinds of assumptions. He never proved anything. Whenever he wanted to differentiate, he assumed it can be differentiated. So it paints him as a person who had a kind of tremendous intuition. At that time, that is what, 120, 130 years ago, the standards of rigor in mathematics are not what they are today. It is because of general feeling that we better be very careful, otherwise we may prove results which are actually wrong. The idea that one should be very careful in proving things in mathematics came towards the latter half of the 19th century, mainly in Germany. And one most important person who spearheaded this move was Weierstrass, whom I mentioned yesterday. So Sophus Lie was working around that time, and you read this book of Yaglom. It's a very beautiful hardcover, green, bright green color. Springer? I don't remember now. Academic or Springer, one of those. So when these results were first found, there was really no sense of rigor which is now associated with mathematics. Okay. So we can say that that equation, partial differential system, which I just rubbed out, if I have a system of matrices, a matrix of functions eta and the inverse psi, which is an acceptable system, and that we will see what acceptability means, then from the functions eta, we can reconstruct groups, the group, at least locally. All right, all global properties are not yet in our hands. So composition law can be defined, associativity will be there, inverse elements will behave properly, and so on. So this is the first of 4 parts of this set of lectures. Now I come to the next. This is also very pretty. One parameter subgroups, abbreviated as OPS, and canonical coordinates of the first kind. Now I might mention at this point that there is a very beautiful set of lectures by Raka given in 1951 in Princeton at the Institute for Advanced Study. And guess who wrote the lecture notes? Merzbacher, the man who wrote the textbook on quantum mechanics. Very nice lectures. However, in those Raka lectures, what we are trying to do now, reconstructing the group from the Lie algebra, is not done. Basically, it is not done. And I remember long ago Mani telling me, our mechanics is the only accessible place where that part is also clearly described. And so, whom can I thank but Bargman? Because in his course, he did this in complete detail. So, which is what I am also going to do. So, it is not just that we will describe a group by structure constants and let it go. Structure constants will come, they will have to obey certain conditions. Then the question always will be, have we discovered all the conditions they have to obey? Is there something else lurking somewhere which we have not found? Given the conditions which seem to be more easily obtainable, is that all that we need to reconstruct a group? That is what I learned from Bargman, and that is what I want to ultimately lead to for you. So, this is a very important concept, one-parameter subgroups. So here we have a Lie group already given to you. And given a Lie group, we define certain objects in it. What is a one-parameter subgroup? It is a family of elements parameterized by one real variable sigma or tau. So for each value of this parameter sigma, you have an element in the group. And you have this composition law. It passes through the unit element at the parameter value 0, and the inverse is changing the sign of the parameter. This is the definition of a one-parameter subgroup in a Lie group. Now, in the rotation case, we know, keep the axis of rotation fixed and consider all rotations by all possible angles. That's an example. Okay. In translations also, keep the direction of translation fixed, but imagine all amounts of translation. Okay. So this is the definition of a one-parameter subgroup, and let me stress, by definition it is an abelian subgroup. Parameters just add. Now we find, we follow the similar procedure, we will find that this idea of a one-parameter subgroup can be expressed by a system of ordinary differential equations. Why? There's only one independent variable sigma, not a partial differential system, but an ordinary differential system. What will we do? Well, you work in your chosen coordinate system. Let these be the coordinates of the group element at parameter value sigma on the one-parameter subgroup. So, at sigma equal to 0, you are at the unit element of the group, so the coordinates will be 0. Now you ask, by how much do the coordinates of the elements on the subgroup change if you go from a point sigma to a nearby point sigma plus delta sigma, first order. Make a small change in the value of the parameter. Well, this is a one-parameter subgroup, so you know, because it is abelian, it is a result of composing A at sigma with A at delta sigma. Obvious, it is from that equation. So, in our coordinate system, you put in the first slot, you could put first or second, doesn't matter, it's an abelian subgroup, coordinates of the element A of delta. Second slot, put the coordinates of the element A of sigma. And now you retain only first order terms in the delta sigma. What functions will you get if you do a Taylor series expansion? You will get the derivatives of the group composition with respect to the first arguments calculated at the identity. What are they? They are the etas. So this will be alpha of sigma eta jk of alpha of sigma delta sigma t, where we define t to be the coordinates of the element A of delta sigma close to the identity. So you can say that we have introduced a thing which we call t. It is the derivative of the coordinate alpha of sigma at sigma equal to 0. So it just tells you how in the group manifold this curve is a one-dimensional curve, how it, in what direction it is starting at the unit element. So now you take this equation, bring this to the left-hand side, convert it into a differential equation, and you will find the elements on a one-parameter subgroup obey this equation, this ordinary system of ordinary differential equations with respect to the parameter sigma. So we say that the t is called the tangent vector to the one parameter subgroup at the identity. So that's the name we give to it. T equals tangent vector to the one parameter subgroup at the identity. That is the meaning. But this now can be reversed. You can start, take any set of real numbers t1, t2 up to t superscript r. You can say, solve this system of ordinary differential equations. This is like a system of first order equations of motion, if you like. There will always be a solution. There is no integrability problem because it's not a partial differential system. It will have a solution, and you can convince yourself that the output of this, the solution of this system of ordinary differential equations is a one parameter subgroup. What is it you have to check? Since I am feeling rather tired, I want to skip some of the steps. We would like to ask, is this equation true? If you take the element alpha of sigma and the element alpha of tau, coming from this system of ordinary differential equations 24, will the product of those two group elements be the element for parameter value sigma plus tau? Do we have this relation? The answer is yes. And how do you prove this? I will leave it as an exercise for you. Call same thing as before. For the moment, suppress tau. Think of both sides as functions of the one live parameter sigma. Find out what differential equation does L obey, what boundary condition. What does R obey, what boundary condition. And in checking the equation for R, you will have to use the system of PDEs for F, which we have already derived. So this I will not prove. I will leave this as an important exercise. Convince yourself that both left-hand side and right-hand side, with respect to sigma, obey the same nonlinear partial differential, ordinary differential equation, and at sigma equal to 0, they agree numerically. Therefore, they are equal for all sigma. So it means we have established a one-to-one correspondence between one parameter subgroups and tangent vectors at the origin. Now it is probably useful to draw a picture. This is the group. Here is the unit element, identity element. You are using some chart, some coordinate system. You choose some tangent vector. So it means that you have determined in what direction you will start moving at the identity. If delta sigma is extremely small, this point will have coordinates t delta sigma for small delta sigma. But you know you have a group in your hands. So if you know this element, you can take the square of this element, cube, higher and higher powers. You can generate a whole curve. The whole one parameter subgroup can be built up. Of course, you will wonder, what about higher order terms in delta sigma? Well, that's why we convert it into a differential equation. You can make delta sigma smaller and smaller and increase the accuracy of your computation. Okay, so given a tangent vector, a vector in r-dimensional real Euclidean space, thought of as the tangent to a one-parameter subgroup, at the identity, the whole subgroup is determined. If you are here at sigma, the inverse might have been here, minus sigma, and so on. And you take sigma and tau, compose them, you will shift to sigma plus tau, according to this rule. So I hope this idea is clear. The concept of a one-parameter subgroup and the concept of a tangent vector to a one-parameter subgroup, they determine each other uniquely. And this is the basis of a very, very important concept which we now come to. You can see that the whole idea is that since you are operating within a group, and it's a continuous group, Lie group, if you determine the direction in which you want to start at the identity, globally the curve is determined. It's just the group composition law repeatedly being used to generate more and more of it. All right. So unfortunately, I rubbed out this equation. Well, no harm done. I will write it again. This is the equation for a one-parameter subgroup. Now we will do the following. We know that once you give me a tangent vector, the components of the vector t, a solution is determined. So let us write the solution for the moment in this form. We will show the dependence on the parameter sigma along the subgroup, and we will show explicitly the choice you have made for the tangent vector also. But you can see that if you scale sigma and you scale t reciprocally, nothing changes. So actually the solution to this system of differential equations, it is not a system of functions depending on one parameter plus one tangent vector. It is actually, and I will introduce a notation chi here, it only depends on the product of sigma parameter and tangent vector tau. The point is that the solution of this system of ordinary differential equations, how many unknowns are there in this equation? How many unknowns? What is the range of this index superscript j? R. So the number of unknown functions is R. How many arguments are there to begin with, very naively? How many components does T have? R. So to begin with, without thinking too much, we said we will indicate it depends in some way on the parameter sigma, it depends in some way on the input T. So initially it might appear we have R functions, each one depending on R plus 1 independent variables. But that's not true. If you were to double sigma and take half of T, nothing would have changed. So this solution to this one parameter subgroup problem, the solution involves only the quantities sigma T1, sigma T2, sigma T3 up to sigma TR. Only R variables. So these will be R functions of R independent real variables. This you must be very watchful. This solution to the one parameter subgroup problem will be of this form. Sigma, it only depends on the product sigma times tangent vector T. What are the things we know about chi? We know that if I were to take 0, I should get 0 because I'm at the identity. And if I take a small delta sigma as the argument, then to the leading order, chi will look like this. And from here, looking at this, you can immediately see after all, it depends only on the product sigma and T. So let me absorb sigma in T, rub it out. No harm done. What can you say about the matrix of partial derivatives of these functions chi with respect to the components of the tangent vector at the origin? Huh? Delta G. You just have to look at this. Correct? So now we say, our good old neighborhood comes in again. We say, this Jacobian matrix is a unit matrix at the unit element of the group. Therefore, in our favorite neighborhood, throughout the neighborhood, we will assume this Jacobian is non-singular. Huh? Beg your pardon? Yeah, but you can show this. See, I am putting T equal to 0 after differentiation. And the dependence is only on the product, T times delta sigma. So for the moment, for this purpose, you may just imagine that I have infinitesimal arguments, delta T1, delta T2, up to delta TR. And this is the result of that. Huh? Okay. After all, doesn't this mean because I have scale invariance, so we will say that we will imagine that our neighborhood has been chosen to obey one more condition, that d chi by dt is non-singular. We will make this assumption over the neighborhood in the group in which we are working. After all, it is a unit matrix identity, and if we don't go too far from the unit matrix, we can hope that we will be sure that it will, because of continuity, it will remain non-singular. Now you do the following. you appeal to the implicit function theorem. And I go back to this picture of the group. It is not the whole group, it is some neighborhood in which all these operations are meaningful. Here is the identity. Take some point A with coordinates alpha in this region. You ask the following question. If I want to choose the tangent vector, it is like aiming a projectile to reach a certain target. Galileo's old problem. If I tell you that I want a one-parameter subgroup which shall pass through a pre-assigned group element when the parameter takes the value unity, can I arrange it? Can I choose my initial direction, the vector t here, in such a way that when I solve this differential equation, I will find that it starts off here, and then it builds up, and at sigma equal to unity, it exactly hits the given, the chosen or specified group element. Question is, can this be done? Can you arrange a choice of tangent vector so that if you think of sigma as a time, and if you say sigma equals 1 means 1 minute, then at 1 minute the curve should reach the given point? The answer is yes. By the implicit function theorem, as long as we know that this matrix is non-singular throughout the region in which we are working, there is a unique way to solve this equation. Given alpha, given any group element in this neighborhood, there is a one-parameter subgroup with a perfectly well-defined tangent vector at the identity, such that that one-parameter subgroup will arrive at the chosen point in the group at 1 minute. You understand what I mean? So you can say that given the right-hand side, the values for the coordinates of the point A here, alpha 1 to alpha r, you ask, can you find for me a set of tangent vector components such that this will happen? Answer is yes, as long as we are in this region where the Jacobian is non-zero. And now it's one more matter of notation. We are thinking of this box as alpha are specified, t are unknown. And t, we are guaranteed there is a unique t given alpha. So let us invent a notation. We will write t as a system of functions zeta of the alphas. Now all this I have learnt from Bargman. So now we do a very, very clever, it's a very beautiful idea, and it is an idea which is used in differential geometry, also in general relativity, in different contexts. So you probably will like it. What is it we have said? If you tell me where you want the one parameter subgroup to be at parameter value 1, I will tell you how to start at the identity. So if you give me the group element, I know what tangent vector to start from. That is what this thing says. Now, it means that in this neighborhood of the identity, every element in the group can be reached on a unique one-parameter subgroup. It's a beautiful result. Huh? This is clear, right? Argument is clear. We now exploit this. We have been working in some coordinate system. After all, we have used functions for parameters for group elements, we have used the etas, we have used the f's, all these things. We now step back a little bit, and we say the element A in the group, which was assigned coordinates alpha, and which you plugged into this equation, and then solved it and got that, we will invent a notation for this group element independent of coordinates. So Beautiful. We will write it as the exponential of t. Now, this is a formal notation. It is not the exponential series. It is just a concise way of what does this say? If A is exponential of t, t is a vector. It's an r-dimensional real vector. What does this equation say? It says A is the group element which you reach if you start on a one-parameter subgroup in the direction t at the identity, and you run along that one-parameter subgroup for 1 unit of parameter. Go up to sigma equal to 1. So this is such a powerful notation. All this information is fed into that. The fact that a one-parameter subgroup is uniquely determined by, what is the time? Oh, should I stop? No, the fact, so many things are built into this notation. The idea that a one-parameter subgroup is uniquely determined by its starting shape, by its tangent vector at the identity. Second, because of this Jacobian thing, if you remit yourself to a suitable neighborhood of the identity, every group element will lie on some one-parameter subgroup, and this expresses that. Okay? So, you can say, at a general point of the parameter, this would be true. I just scale t. I would say this is true for another value of the parameter. And what is the group composition law? This appears in this somewhat formal notation as this. Correct? Correct? Both sides at this moment have to be viewed as somewhat formal, but now you understand why this notation is invented, because it is so much like the exponential function. So I formal exponential. So this is the power series. The t is a vector in an r-dimensional real space, linear space, and we are defining what we mean by the exponential. It's a finite group element. So it's a kind of a non-local connection. You say how you want to start moving at this point. For infinitesimal parameters, where do you reach from the identity? Once you know, then group composition. So you might have started with delta sigma equal to 10 to the minus 6. Group multiplication can be applied any number of times. Do it 1,000,000 times. Within some accuracy, you will reach some point here. And you want to make it finer and finer, you can do that. In differential geometry, the similar idea is used, that given a point, a geodesic is uniquely determined, at least locally, by the initial direction. And now you can say, start from some point, think of it as, for the moment, as origin, and you can ask, in some neighborhood, can I say that each point in the space lies on some unique geodesic starting from here in a well-defined direction? If so, those components of the initial tangent vector to the geodesic can be converted into coordinates at that point. Okay, so I'm jumping a little bit. So this is what is called Gaussian coordinates or normal coordinates. Some such name is there. So it is a very similar idea. In the differential geometry case, with a metric and so on, instead of group composition, you have the concept of geodesic, which is a system of second-order ordinary differential equations. Yeah. Yeah, you know, in the rotation group it is true. You rotate by 2 pi, you will come back.
So in that case, say my So,
Yeah?
then in that case I will have two paths.
Yeah. So, in order that things work well, please limit yourself to a certain region around the identity. Don't go all the way to 2 pi rotation. Limit yourself, maybe at not more than 150-degree rotation or some such thing. Then within that portion of neighborhood of the identity, there will be a one-to-one, a unique one-parameter group, starting from E and reaching any point you want. So this whole thing is local. If you do things globally, there can be multivaluedness of some kind or the other. That is correct, and what you asked is quite correct. So actually, since I am rather tired, I will stop at this point, and I just want to make some passing comments. This is not in my notes, but it is just interesting. What you can see, so this is just to help your imagination. Those elements in this neighborhood which lie in these one-parameter subgroups, in a representation, they would be represented by single exponentials, e to the power some parameter times the generator. That would be an honest exponential. You can actually say the exponential is 1 plus the thing plus square over 2 factorial and so on. At this point, it is a formal exponential. In a representation, this formal exponential becomes an honest exponential, but the thing in the exponent is a square matrix. It's not a vector like this, it's a square matrix, so powers are defined. And so it becomes an honest exponential infinite series. Then another thing can be asked, are there some groups, so I can say any Lie group, so provided you choose the neighborhood reasonably carefully, every element in that region lies on a unique one-parameter subgroup with a well-defined tangent vector at the origin. The question can be raised, can you expand this neighborhood? Can it be made to cover the entire group? Is it possible to say that every element of the group can be reached on a one-parameter subgroup and uniquely? Now, in the SO3 case, we know it's not true. If you go pi and minus pi, they are the same. In SU2, it is even worse. Everything at radius, what is it, 2 pi, is the same element. So you must stay away from those boundary regions of SO3 or SU2 if you want to have a one-to-one statement that every group element can be regarded as an exponential in this sense. This is called the exponential map. It's a very important word. What does it tell you? It says, take all tangent vectors at the identity. It's a real linear vector space. You can map all of them within some bounds, within this neighborhood, to group elements. You should not take tangent vectors with arbitrarily high components. Then you would be possibly hitting trouble about multivaluedness and so on. So, provided your components of tangent vectors do not become arbitrarily large, it is true that there will be some neighborhood of the identity which you will get as a result of this construction. That is called the domain of the exponential map. So exponential map at this moment is it's a concept in Lie group theory. It takes one-parameter subgroups, takes the tangent vectors, and invents finite group elements from tangent vectors. It's a very beautiful idea. What is the secret behind it? This ordinary differential equation, the solution of this for finite parameters. So now there is an interesting question that there are some groups, this is just by the way, just to spend some time, there are some groups with the property that every element of the group globally is reachable on some one-parameter subgroup. There are some groups which have this property. Such groups are called groups of the exponential type. A great name. So a Lie group is said to be a group of the exponential type if every element of the group, without exception, can be reached on some one-parameter subgroup. We don't insist it should be unique. We just want some one-parameter subgroup. That will mean that the exponential map ultimately covers the whole group. But there are groups for which this fails. And there are very elementary things, which we will see some time later. If you choose a sufficiently small region of the group around the identity, everything can be reached on one-parameter subgroups. But there are portions which you cannot reach on one-parameter subgroups. They are all connected, not simply connected. They are connected, not simply connected. So there are groups where this construction does not lead to the entire group manifold. So those groups are called not of the exponential type. And the only reason for saying it is that Simon and I wrote some paper about it in honor of Biedenhahn, and he had not known this concept. So he appreciated that he learned something from what he wrote in his honor. So I'll stop here. I hope I'll feel better tomorrow.